Yeah, good afternoon, ladies and gentlemen. It's my honor to welcome you all to the very first webinar series by Spinco Biotech, Sharing the Learning. So we have published more than 100 articles of sharing the learning in our technical journal, Cutting Edge. And now we are bringing you live the same insights, latest innovations, and expert advice in the form of a webinar. As you all are aware, Spinco Biotech is India's leading analytical instrumentation company, started in 1981. True to its tagline, Spinco is bringing technology and enabling science for the past 41 years. Customerization, a term coined by our chairman, is to delight our customers at every touch point. Customerization has been the cornerstone of our company culture. So coming to today's topic of the webinar, an overview of modern HPLC with a flavor of basics. HPLC has been one of the defining techniques of the last 40 years, and its importance and range of uses are likely to increase in the coming years. The modern HPLC has come a long way from its commercialization since 1970. Today's webinar, we are going to cover the basics of HPLCs to its modern avatar. So it gives me immense pleasure to welcome Dr. Manohar to this webinar. He is an eminent personality in the analytical world with over 4 decades of experience. Dr. Manohar is currently the director of Indian Institute of Chromatography and Mass Spectrometry, an institute at Chennai developing experts of tomorrow in chromatography and mass spectrometry through training. He has been practicing analytical science over a period of 45 years at various multinational companies. So after obtaining his PhD in physics from University of Madras, prior to this assignment, he has been a senior vice president in Piramal Life Science Limited for the past 6.5 years. He was responsible for setting up the entire facility for drug discovery research as well as diagnostic research laboratory. So what better person to give us insight and experience on HPLC? So with this brief introduction, now I hand it over to Dr. Venkat Manohar. So before that, some housekeeping rules. I request all of you to please type in your questions only in the QA box so that we can answer your queries at the end of the session. So over to you, Dr. Manohar.
Are you able to hear me?
Yes, sir.
I shall share the screen. Are you able to see?
Yes, sir.
Excellent. Thank you, Mr. Satish, for your nice introduction on sharing the learning and also about me in giving this presentation to many of our participants. I am very happy that there are more than 100 participants sitting and listening to our presentation. This is the first of its kind. When we do experiments, we share with our learned colleagues and our scientists across the country and elsewhere. When we 12 years back, when Mr. Tyagarajan was having an idea of starting the Cutting Edge journal, one of the suggestions and requests he made to me was, can you write some article in this Cutting Edge journal? I said, whatever I have learned over the last 3.5 to 4 decades, I can share with as a part of article, but with a condition. He was a little bit surprised. What is the condition you are going to put? The condition was, unlike a conventional review articles, I like to write the article in Cutting Edge based on the experiments and results and interpretations that we do on various molecules that we work in the laboratory to a level of standards of international standards where the publications can be peer reviewed by many of the colleagues. He was very happy to accept he said it's not a condition, but he said it is this is what I am looking for. If you are able to do experiments in the laboratory which at IICMS, at Indian Institute of Chromatography and Mass Spectrometry Laboratory, it will be an excellent value addition to our people because they can see what they learn. So all the publications which we have incorporated in sharing the learning after the last 10-12 years in cutting edge are all the experiments that was carried out by our team at IICMS, and those data interpretation has been shared in the sharing the learning. While doing this entire activities, I am grateful to Shimadzu for giving us, and as well as the Spincotech team for giving the HPLC, LCMS, the new latest instruments getting installed in our laboratory where we carry out this kind of experiments and do all this kind of activities which went to the publication level in cutting edge. Further, some of the works we presented in international conferences such as American Society for Mass Spectrometry, and everywhere we made presentations, and one of our presentation on gemcitabine has been accepted for oral presentation, which was presented none other than Mr. Aravind Tyagarajan, the joint managing director of this company, some 10 years back. So today I am going to share, or in the coming days, we are going to have a series of webinars where we will share with you all the data and experiments that we have done in this kind of, in using HPLC, mass spectrometry and other techniques. And also we share our feelings, our learnings with you in the coming days. With this brief, I once again thank Satish and his team for arranging such an excellent opportunity for our young generations to learn about the HPLCs and chromatographic techniques as well as mass spectrometry. When I wanted to give a talk, when Satish requested what kind of topic we'll prefer, can you suggest a topic? Then I thought that many of our people, our customers, our colleagues, our scientists who work in the laboratory, they work day in, day out, mostly using the techniques, and they do focus on their product analysis. In that entire process, there exists a probability sometimes they need to brush their basics so that when they do analysis, they can accelerate the data delivery to their organizations. Therefore, I suggested Mr. Satish and his team, I will start the presentation with a small flavor on basics of what all of us have learned in our graduate days and postgraduate days. And then based on the brushing up, we shall go into what today a HPLC can deliver to us. Now, in this presentation, what I will do is, I will talk about the basics of HPLC a little bit, followed by in the new normal, after the COVID days, where we have been told to work from house, as an analytical chemist, how I can work from home, or to extend it, today, can I work from anywhere? To answer those questions, I will share with you what kind of HPLC that we are using in our laboratory and what it can deliver to us, what we have learned, and that we will share with you how we are able to deliver to you all, to people by sitting at home or sitting at elsewhere, how these modern instruments can deliver a lot of things to us. With this brief introduction, let us enter into what is called the basics of HPLC. So when you move into the basics of HPLC, I will share the slide once again so that I can move the slides.
So in the meanwhile, can we have a poll question, sir?
That will be much better.
Yeah.
Probably we can ask questions. I request you to ask questions to share the poll questions.
Yeah. So the first question, just to brush up your knowledge, the reverse phase HPLC operates on the principle of. So you have 4 questions, 4 answers: ion exchange, size exclusion, hydrophilic, hydrophobic. So the poll will be open for another 1 more minute. You can give in your answers. The reverse phase HPLC operates on the principle of ion exchange, size exclusion, hydrophilic, and hydrophobic. So we'll end this poll now. So we have got the results. So 45% believe it's hydrophobic, 21% believe it's hydrophilic, and 9% believe it's size exclusion, and 25% believe it's ion exchange.
Okay. Based on this feedback, shall I proceed now?
Yes, sir. So this answers, you will be answering it in the coming slides. You will be answering this question in the coming.
Yeah, well, during the presentations, I will try to answer some of them. This question. Now, to introduce before we go into this poll question, let us brush up ourselves with the basics. There is a Chinese proverb which I want to share with you. The proverb says, I heard, I forgot, I see, I remember, I do, I understand. Why I should share this proverb with you? Several times, when somebody talks to us, we hear, afterwards we may not remember, we forget. Sometimes we see certain things, but we'll remember for some time. But when you do something on hands-on, for example, this chromatography business I started 45 years back, even today, I remember my first analysis, how to prepare a sample, for an analysis by gas chromatography, how to dissolve the sample, how to use a manual injector. I even today remember. That is because the hands-on or what I do is very important. When I share the information in our presentation, it is as if all of you have done. Therefore, in my opinion, you will understand the presentation. Therefore, we will discuss to begin with what is a basic chromatography and followed by what is modern HPLC. You know, the basic HPLC comprises of a solvent delivery system along with a pump. You have an injector port, you have a column followed by a detector with a waste collection and a computer to acquire data. But I will not discuss about it because you are using day in, day out. A modern HPLC is completely different from this basic HPLC. It has this basic HPLC plus lot of features incorporated in that. We call it as modern HPLC. If you look at this chromatogram, it has got so many points. One, first of all, it has a parameter, what is called, if you see here, a tangent drawn along with the graph, a point of inflection, and also a baseline. This is a typical chromatogram which you see day in, day out. When we enter into the chromatography, we use certain terms. Some of the terms that we use are, one is called dipole moment, another is called polarity, third is called absorption. When we talk about the dipole moment and polarity, what do we mean by dipole moment? What do I mean by polarity? If you recall your graduate chemistry, you will talk about the electronic charges and nucleus. Now, there exists the distribution of charges. When the charges distribute or non-uniformly they are distributed, there exists a net negative charge that does not coincide with a positive charge. Such a distribution where net charges are separated by a distance is called dipole moment. Now, if mu is called dipole moment, if Q is the net charge and R is the distance between the both the positive and negative charges, then dipole moment can be given as a product of two, which means that it can be a product of charge and the distance between the two R. This is how we represent a dipole moment. Net charge separated by a distance is called dipole moment. What do you mean polarity? It contains different physical properties. Polarity is nothing but separation of electrical charges which leading to a molecule or group of chemicals having electrical dipole moment with negatively charged end and positively charged end. That is, the polar molecules contain more or one more or more polar bonds because of the difference in negativity, electronegativity between the bonded atoms. Therefore, polarity is defined as a separation of electric charges leading to a dipole moment, leading to a molecule, and with net negatively charged at one end and positively charged at the other end. Therefore, if I say, can I have an example for that? I will show an example. That is an ability to form the hydrogen bond. For example, in this case, in the case of ethanol, there is an OH at the end, which means there's a hydrogen bond is polar. If we take a diethyl ether, there is a methyl group at the end where there is no hydrogen bond. On the other hand, if you take these two molecules, acetone and isobutene, in the case of acetone, there's a C double bond O, isobutene is here, carbon double bond is there, C and CH2. In these two cases, isobutene is not polarized, whereas acetone is more polarized. Therefore, larger the dipole moment, higher is the polarity. The thumb rule to predict the polarity of the molecule is if all similar regions are not same. Please remember, if all similar regions are not same, then the chemical species is polar. Now, if all similar regions are same, the chemical species are non-polar. If all similar regions are not same, the chemical species are polar. Therefore, if that is the case, now I have defined what is dipole moment. I have defined what is molecular polarity. I showed a couple of examples. Now, the third term which we are supposed to understand is molecular adsorption. This molecular adsorption is related to the surface chemistry of a molecule. In the case of a chromatographic technique, we normally encounter the phenomena what is called surface adsorption on the, that is, I have a stationary phase, I have a mobile phase, I have a compound. Now, all that if you imagine a triangle, in the triangle each corner at one end you call it as sample, at the other end of the corner you call it as a mobile phase, at the third end you call it as a stationary phase. Now, when you have a sample, the sample will undergo, when it enters into a column, to using your mobile phase, the sample gets adsorbed to the surface of the stationary phase. Now, depending upon the nature of the absorption, the compound will stay for a longer duration with the stationary phase or shorter duration with a stationary phase. This kind of absorption, we call it as physico-absorption or physical adsorption. There is another type of absorption called chemi-absorption. What do you mean chemi-absorption? I will first let us define physical absorption. If the bonding between your compound of interest and the stationary phase is very weak, is only a kind of van der Waals type of interaction where there is no significant redistribution of electron density, such a kind of absorption is called physical absorption. That is, there is no significant redistribution of electron density. On the other hand, if there is a rearrangement of electron density, the bond is called chemical bond. It can be ionic in nature or it can be covalent in nature. Then it becomes a different compound. In the entire chromatographic process, the adsorption is physical, not chemical. Because in the physical process, because of weak binding, depending upon the affinity, the compound is getting stick to the surface of this mobile stationary phase. When the mobile phase comes, if the solubility of your compound in the mobile phase is greater, the compound is getting dislodged from the surface and it would start moving from the stationary phase. Therefore, in chromatography, the nature of the binding is physical absorption and not the chemical absorption. I can represent the form of a picture. Now, if you see this picture, the red color shows you chemical absorption where the energy binding energy is very strong. Whereas in the case of physical absorption, the violet color you can see the physical energy is weak, very small in number. Therefore, if energy is small, there you can easily dislodge the molecule. Energy is large, there's a redistribution of the electron, therefore it becomes permanent, therefore the compound may become a different compound. Therefore, physiabsorption is very important for all chromatographic separation. In addition to that, we normally use some of the terms in chromatography. One is called stationary phase, which I explained just now. The second one is what is called mobile phase. I told you just now. It can be a liquid, it can be a gas. The third one, I call it as the process of interaction of your sample, mobile phase and stationary phase is called the process of separation, or it is called elution. The fourth term is called the mobile phase itself can also is called eluent. The sample can we call it as eluate, which is supposed to be, it can be a mixture of compounds, it can be a single compound. Now, to what extent the sample is getting stick to the surface of the stationary phase, or the extent of eluate sitting on the stationary is called a retention, or the duration is called retention time. Can you explain this entire separation in the form of a experiment? This is a kind of experiments which comes in my mind. You can see a burette here, and the burette, the bottom is there's a glass hole which is plugging the burette outlet. Are you filled with a solid material which is nothing but your stationary phase? You put a sample solution, pass it to, and then use some solvent, which is pour some solvent. When the solvent is poured here, you can see here it's slowly eluting out through this path. Now I can collect the sample one by one. Now, if this sample is a mixture of components, you can see here, it can be contain component 1, component 2. Now, depending upon the physioabsorption or the amount of energy it possesses to stick to the surface of this solid material, one compound will preferentially be remaining in this column for longer duration, whereas one which is not able to stick to the surface will start moving very fast because of the mobile phase. Thereby, there is a preferential migration of the sample with the mobile phase, which will start flowing and causing the separation between the component 1 and component 2. Now, the flow of the solvent is by gravitational force in this experiment. Therefore, both the components are separated. Good. Fine. We can nicely separate the components. Now, you have to understand one most important term, what is called distribution ratio. What do I mean by that? When a component contains a mixture of compounds, now in this mixture, say component 1 is a component 2. To what extent these components are distributed between the stationary phase as well as the mobile phase. That ratio plays a very important role, and it affects the separation efficiency of the column. Therefore, when the sample, which is nothing but eluate, is transported by the mobile phase over a stationary phase, there is a rate competitive association and dissociation of the mixture of compounds. And this rate competitive association dissociation causes the distribution between the stationary phase and mobile phase, and it is defined as partition ratio or partition coefficient, which means K. If K I define as a distribution ratio, AS by AM is what is called the concentration of the sample in a unit volume of the stationary phase to the unit volume of the mobile phase. If I know this ratio, it plays very important role that influences separation. Therefore, the entire retention behavior is determined by the distribution constant of the sample, which means what kind of interaction that is taking place between the stationary phase and your compound determines how long the compound is retained in the stationary phase. It can be a hydrogen bonding, it can be a dipole-dipole interaction, it can be electrostatic interaction or ionic interaction. In addition to that, there are all physical parameters such as temperature, viscosity, diffusion coefficient also plays an important role. That is why your column is always kept in a temperature controller unit, which because that influences the separation efficiency. Another most important parameter which affects the retention behavior is the mobile phase flow rate. Because in the case of a mobile phase flow rate, the velocity with which the mobile phase flows plays very important role, because the concentration of the mobile phase is determined by the rate at which it flows. And not only that, the volume of flow also plays a very important role. Therefore, the dimension of the column, namely the diameter or the surface area, plays an important role. So all these parameters put together influence the separation. Now, I introduce a term called zone migration. What do I mean zone migration? When a sample elutes through the column, it does not come as a single particle. It comes as a form of a band. The band is called a zone. And the effective migration, if that means the entire compound in the form of a zone, in the form of a band, can be determined by a concentration of the sample, how it comes. Therefore, the concentration of a compound at a given time t, Ct, can be defined in this form of an exponential equation. If you do that one here, how much it depends upon the flow rate F. It also depends upon that how it elutes, and most important thing is the retention time of the compound. That is why you get a distribution here in the form of a Gaussian peak. This is where the peak starts, the peak increases, the peak reaches a maximum, it comes down, again comes down and ends. Peak starts, peak ends. Now peak reaches a maximum. This is called upslope, this is called downslope, this is called apex of the peak. Now this entire region, we call it as a band or a zone migration. This is how we define the theory. How do we arrive at this equation? Don't ask me, because I have to give a separate lecture on this for a couple of hours. This point of where the apex is called point of inflection. Why I call this a point of inflection? You draw a vertical line here. If I draw a vertical line here, you take this peak on a piece of paper, draw a vertical line at the apex and fold it. When you fold it, it will exactly match either if the peak is symmetrically comes out of the column. And that is why this is called point of inflection, defined by so many parameters. And then the peak shape is very, very important in chromatogram, because the peak shape tells you the ability of the compound or the kind of van der Waals force of interaction or a hydrogen bonding or dipole-dipole interaction, which is responsible for binding your compound to the surface of the stationary phase. Therefore, and this only is getting affected to what extent? Sometimes your peak increases very fast, decreases very slowly, or your peak increases very slowly, decreases very fast. All kind of unsymmetrical things. In a chromatogram, you are able to see day in, day out. All plays very important role, and it is defined by peak shape. For example, the FDA authorities look into this parameter very, very carefully, whether a chromatography system is working properly or not. Peak shape is very, very important. Now, as I told you, this is how you draw a tangent in the upslope, another line at the downslope, the tangent at the point of inflection, and this defines a chromatographic peak. Why I should draw this tangent? You do quantitative analysis to determine how much my compound is present. Is it 99% point pure, 99.98% pure? If that or it is impurity is 0.02%, 0.002%, how much is the impurity concentration? Such a kind of quantitative estimation of the purity of your compound or the impurity content, you have to determine the area under the curve. How do you determine the area under the curve? Very, very simple. When I draw a tangent, if I draw a baseline here, now what happens? This is a upslope, downslope, there's a baseline. It's a triangle. What's the area under the curve? The area of the triangle. What's the area? Off into base into height. That's all. This is what your data processing unit, your computer, your software, everything calculates. What they use? Basically, it is an area under the curve. If you approximate the area, it is half into base into height. Whatever the modern computer use, it does everything automatically. And in my days, when I was young like you, at that time, I manually calculate. That's a difference. That's only a difference. This is a typical chromatogram. You might have seen day in, day out. Now, how do I connect the peak shape and column parameters? I have defined your capacity factor. But what I have not defined is what is called selectivity, alpha. What do you mean selectivity? Very simple. If I have got two components, component 1, component 2, which I showed a few slides back, I have to separate between the two. When I separate, what extent they are well separated, because peak alludes in the form of a band or a zone. Is the zone is completely well separated or partially separated, or they overlap with each other? Such a kind of ability of overlapping or ability of well separation is determined by this selectivity factor alpha. That's a zone migration. It depends upon the velocity of the flow rate of your solvent. It also, and I can define the velocity as initial velocity multiplied by 1 divided by 1 plus distribution ratio K divided by sample in the stationary phase and volume of the sample in the mobile phase. And all depends upon the length of the column L and the retention of the compound TR. Therefore, velocity is equal to L divided by TR. Initial velocity is equal to L divided by T naught. All these equations define the selectivity factor. How does it define the selectivity factor? Compound B divided by compound A. TR minus T naught, retention time of compound B minus initial time T naught divided by the retention time of compound A minus T naught. What is this ratio? If a peak is well separated, we call it as this ratio should be more than 1.5, which we call it as resolution factor. I will show you a graph, A and B, resolution 0.75. Again, A and B, resolution is 1, well separated, baseline separated, 1.5. This is what US Pharmacopoeia or the FDA, all these audit people look in your chromatography when they come for audit. Or your resolution is 1.5 or not, with respect to impurity, but the impurity is 0.01%. This is what you look for. Excellent. So these are the summary of the chromatographic parameters. These are the parameters which we talk about in terms of various calculated derived quantities, relationship, and you can see resolution. I can have number of theoretical plates and so on. At this point in time, I like to ask you a few questions that probably, in case, if you have any question to ask me, you can post your questions. This is a basics where I have introduced you some of the terms used in chromatography, namely dipole moment, and then polarity, and then adsorption. I also defined you what is a zone migration. I also explained to you what I mean by selectivity or a resolution factor. Now, do you have any questions? I give you a minute or so to post your questions in the chat box. I request Satish to ask any questions. You can put some poll questions also if you want.
Yes, so we have a few questions. So Mr. Jai Patel asks, distribution ratio means capacity factor?
Yes.
Does distribution ratio means capacity factor?
Correct.
Yeah.
Capacity factor.
Yeah. And QAPC asks, why we don't get proper resolution in peaks?
There are, first of all, in this entire exercise, the most important thing is your sample solubility in mobile phase. If the sample does not dissolve completely in your mobile phase, sometimes the insoluble material which does not pass through the column will sit on the top of the column. And this is one of the causes where it can cause an asymmetry in the migration of the compounds through the column. This is one reason. Second reason is your mobile phase, depending upon the mobile phase, particle size, things will completely be different. And third reason, during the stationary phase, and third reason is, most important thing is, the column packing density plays important role, and the surface uniformity of the column stationary phase also is very important. These are some of the parameters which affects the symmetry nature of the peak that eludes out of the column.
So the other question is from Achi Reddy. So he asks, how can you control late eluted peak misbehavior? How can you control late eluted peaks misbehavior?
Nice. One of the problems in the late eluted peak is that peak broadening is larger because they stick to the stationary phase for a longer duration. When they're getting dislodged from the mobile phase, the rate of migration becomes non-uniform with respect to the particles sticking to the surface of the stationary phase. Therefore, what we normally do is we have to increase the flow rate of the mobile phase at late by doing the programmings in the in your HPLC conditions.
So the next question is, why peak shape is triangle only?
Actually, triangle is a simplification of the peak shape of a chromatogram. Actually, the peak shape is not exactly triangle. At the bottom, there is a small curve you can see in the peak, where the peak is getting smeared when a compound is actually dislodged from the stationary phase. The flow of the particle follows different pathways for each particle. When it follows different pathways, all the particles do not come out of the column simultaneously. Therefore, there is a small smearing at the bottom of the either when the peak is rising or when the peak is completely eluted. Therefore, it is not the triangle is nothing but the approximation of the peak eluting out of the column.
So there are a few more questions, so we can come back to that one. So in the meanwhile, we'll post a poll question. So if you can see on the screen, so what do you feel is the heart of the HPLC? Is it the pump, the detector, auto sampler, or the column? So what is the heart of the HPLC? Is it the pump, the detector, auto sampler, or the column? Yeah, 10 seconds. Okay, so stop the poll. So 64% of them believe the column is the heart of the HPLC, and 1% believe it's the auto sampler, and 13% believe it's the detector, and 22% believe it's the pump, which is the heart of the HPLC. So over to you, sir.
Excellent. I think I have done my job.
Yeah.
The panel, all the participants are attentive and very nice that they have been very well brushed up with their basics, where the answer is true. Column is the heart of the entire system. And having agreed with many of the participants, now what are the types of columns that we are going to use? This is where, depending upon the nature of the column, we can classify chromatography into 4 or 5 types. That's what I'm going to show you. One second. There's a small hitch. Based upon the simple process of separation and distribution ratio, the chromatographic process can be classified as follows. One is called adsorption chromatography. Second is what is called partition chromatography. Third is called ion exchange chromatography. Fourth is called size exclusion chromatography. What I have shown you in my previous few slides examples, they are all adsorption chromatography. We will see one by one what it is. It is just a brush up. I am not going into full details of all these things because each topic, for example, absorption chromatography itself require around 45 to 50 minutes. Partition chromatography, I need at least couple of hours. Ion exchange and size exclusion, each needs 1 hour to 2 hours presentation, because these 4 words, 4 bullet points is nothing but a mixture of presentation consisting of more than 150 slides. But I will not do it here because of want of time, and that's a completely different topic by itself. Let's go very quickly. In the case of absorption chromatography, the equilibration between the mobile phase and stationary phase provides the separation. The mobile phase is a liquid. In the case of a liquid chromatography, the stationary phase is a solid. It's an inert solid, silica, nothing else. Inert silica filled of defined particle size, defined particle shape, and defined particle density. For a defined length of the column, it is filled. And that is why we don't do it in the laboratory. We can get it commercially. The separate method of doing it, people do it and sell the columns. Here, the solute is adsorbed to the surface of stationary phase for some time, and after some time, it is getting dislodged, as I showed in the examples. Now, next is what is called here, the increase in mobile phase of polarity reduces the retention. Remember this. More polar the solute, the greater is the retention. And if you want the compound to get rid of the column, you have to increase the polarity of the solvent. And if you increase the polarity of the solvent, you start from hexane, you can go up to methanol and things like that. We normally don't use water in this kind of columns. This is called normal phase chromatography. The second one is called reverse phase chromatography or partition chromatography, where a thin liquid film is coated on a solid surface. Here, the mobile phase is a liquid, stationary phase is also a liquid. It is called liquid-liquid chromatography. What does it do? The sample dissolved in liquid phase will sitting on stick to the surface of the another liquid coated on the solid surface. How does the separation occur? You just reverse. Want to reverse? The polarity of the solvent is more polar, and the polarity of the stationary phase is non-polar. That's all. Here, the increase in mobile phase polarity increases retention. The strong interaction between the mobile phase and solute makes the compound comes out of the column. If the compound is more polar, it elutes first. Like. That's all the concept.
So I think we can answer the poll question. So the first question we asked for, so the reverse phase works on which principle? So is it hydrophobic, hydrophilic, ion exchange, or
when you say, yeah, hydrophobic means the compound does not dissolve in water, correct? That is what is called hydrophobic is. If the compound is able to dissolve, it is called hydrophilic. That is, if the compound solubility is very good in water, it completely retained in the column for a longer duration because the polarity takes longer time. Therefore, we normally use, it depends upon the polarity, because in the case of a reverse phase principle, the principle is not hydrophobic or hydrophilic. It is based on how competitive your compound is between the solubility in your organic phase, in your water phase. In your water phase, it more dissolves, it remains for a longer duration depending upon the polarity of the compound. Therefore, increase in mobile phase polarity, increase the retention time. If I want to do a better separation, you have to increase the polarity where you have to water as a mobile phase, which means the compound you have to make it more hydrophilic in nature. Okay? Am I right? We will discuss. If any question is there, we'll see them in the question answer session. Okay, next one. What is called ion exchange chromatogram. In the ion chromatography, there are 4 types of ion chromatographies are there. One is called ion suppression chromatography. The second one is called ion interaction chromatography. The third one is what is called ion exchange chromatography. The fourth one is called ion exclusion chromatography. I will show only the example of ion exchange and not anything else, because rest of things is a different technique by its together. It involves a lot of theory behind it. This is an example of ion exchange chromatography where the mobile anions held near cations that are covalently attached to the stationary phase. In the case of ion, for example, if the ion exchange, it can be a positive ion, it can be negative ion. If it is a anion exchange means positive ion exchange, cation exchange, negative ion exchange, which we talked about, where the charge exchange occurs on the surface by which you provide the separation. That is why in many this ion exchange chromatography mainly used for inorganic analysis. Sodium ion, potassium ion, lithium ion, calcium ion, magnesium ion, all these things can be separated by this kind of ion exchange chromatography. Size exclusion chromatography is one which depends upon the molecular weight of the compound. It is very, very useful technique to characterize molecular weight distribution of the polymers. For example, if you look at this chromatogram, large molecules are excluded with interaction to the surface. Small molecules penetrated the pores where it will live for a longer duration. Therefore, large molecules eludes first. Therefore, by which you segregate the separation based on the molecular weight of the compound. The third or fourth one is what is called affinity chromatography, where a compound, this is mainly used for protein analysis, where one kind of molecule in a complex mixture becomes attached to the molecule that are covalently bonded to the stationary phase. In this case, the immobilization of antibody and reactions in protein can be separated by this kind of applications, mainly for used for protein separations or extraction of protein compounds from your enzymatic reactions. Now how do you select the column based for method development? I'll give one small table. Before we go into that, I will tell you what are the various parameters and specifications. For example, if you are depending upon the separation, you can see here that the flow rate, if it is high, depending upon, there are various parameters controls the column is flow rate, particle size, column length, mobile phase, capacity factor, and dead volume. If the flow rate is high, your separation efficiency is high. Particle size is smaller, theoretical plate is high, therefore efficiency is very high. Similarly, column length, similarly viscosity. If the viscosity is low, separation becomes much better. Similarly, the retention time or the capacity factor is low, less than 2, then separation becomes very poor. Now, the dead volume is low. This is also one of the reasons for peak broadening. Normally, the commonly used HPLC columns are adsorption principle. It is silica columns, alumina with irregular shape with the particle size 5 to 10 microns, 20 microns. Reverse phase column with the C18, C8, C1, C3 and so on. These are all non-polar components as a liquid phase coated on the silica. In the case of a normal silica, the kind of treatment we can do what is called ester, ether, diester and so on. We can also do amino columns. We can do cyanide columns. There are so many type of columns we can use. Nowadays, core shell columns are in the picture and also chiral phase columns. I will not touch those topics now. This is a very important table. Please remember that which functional group present in the compound will have got higher retention in C18 or in silica. If I use hexane, for example, as a mobile phase with the chloroform, if the compound contains hydroxyl group, first of all, solubility is an issue. The number 1400 shows very clearly that the compound is retained for a longer duration. Or the compound does not dilute out of the column at all. On the other hand, if you look at the OH with the acetonitrile with the 0.2, the K value is equal to small, therefore the compound dilutes first. More polar compounds forms in the reverse column. This table will tell you how do you choose your column. For example, if it's a water-soluble compound, I go for what is called the reverse phase column or reverse phase ionic, depending upon the nature of the compound. And sometimes molecular weight is less than 2000, you also choose for organic solvent for adsorption chromatography. Molecular weight is more than 2000, always better to, for example, protein molecules or a polymers, better, which is water soluble, better go for gel filtration or reverse phase columns and so on. This is how a normal, a conventional table when unknown sample is given to you for column selection. So this is a kind of columns we normally use in our various applications. This is for preparatory HPLC. This is for small columns used for analytical HPLC. Okay. I have till now brushed up a small introduction to just brushing up various types of chromatograms. Is there any questions at this point in time?
Yes, sir. I'll just read out. So one Mr. Tyagarajan asks, what is the correct peak? How do we define good peak in a single sentence? Please explain.
Pardon?
What is the correct peak and how do we define a good peak?
Yeah, good peak is one where at the point of inflection, if I fold both the ends, they juxtapose with each other, which means at the point of inflection, if I draw a vertical line, the distance of the peak start, the distance of the peak end, both are identical, then it is called a good peak.
The second question is from Saujanya. She's asked, is resolution factor directly proportional to the number of theoretical plates?
Yes, yes. It is not directly proportional. It depends on other parameters also, but generally it is directly proportional to theoretical plates.
So one Mr. Santosh asks, so could you briefly tell us about theoretical plate count?
Okay. What is theoretical plate? Very simple. I will give an example. You take acetone as a solvent, take toluene as a solvent. Or I give one more example. Take hexane, take toluene. because both are they both are linear compounds. When I say they are all CH2 groups, they are miscible very well miscible. The difference between the two solvents is boiling point. Toluene boiling point is nearly 110 degrees centigrade. Hexane at room temperature will evaporate very fast. Mix both the solvents. Keep it in a rotary evaporator. Slightly heat it. Don't reach 200 degree, but reach temperature 30 to 40 degree. You can notice hexane will come out, toluene will remain there. So what I have done, I have distilled hexane from toluene. Because I had kept the temperature around 40 to 45 degrees centigrade, the completely entire toluene has been distilled. One distillation cut at a given temperature I made is called one theoretical plate. In a HPLC column, when I say theoretical plate is a 15,000, the column has an ability to do 15,000 distillation cuts, which means theoretically the compound can distill 15,000 different compounds if they are able to behave like a distillation unit. Therefore, a theoretical plate is nothing but is called a distillation unit. If I got a two mixture of compounds, I distilled component 1 from component 2 using the property of adsorption. Therefore, a theoretical plate is called one distillation cut.
So the next question is, what is dead volume and how do you calculate dead volume? From Simon.
Probably what I suggest is to answer this question, I have to show him an example of the calculation. Such a slide is not, I have not incorporated in this presentation. Probably we will have in our series, the coming days, we will have a presentation on how to do method development, how to reduce the dead volume. At that point in time, probably I can give a right answer to this question.
Sure. So we can come back to the questions later, so we can continue the presentation.
Okay. The last part of the presentation is what is called the key of entire presentation, where we talk about what is called the modern HPLC. What do you mean modern HPLC? Before we go into the modern HPLC, all of us the last 2 years are facing a big problem. The problem is COVID. It's a problem, but it has given a new way of leading our life. The biggest advantage of COVID, I don't talk about the other aspects. What did COVID taught us? Can you change your lifestyle? The answer is yes. In every walk of life, we change our lifestyle. We wear a mask. We maintain a social distance. We wash our hands frequently. We take care of our children not to take quite often to the park. We don't take them quite often. We cover the cheek. When some guest comes to us, they make a phone call and come. We don't entertain functions. We don't accommodate more than 50 people. We don't accommodate more than 200 people. life has become totally different. So also our working place. The organization tells us, please work from home. Don't come to the office. Don't spread the disease. The analytical chemist also told to work from home. But the analytical chemist says, I have to prepare my mobile phase. I have to inject my sample. How I can do by sitting at home? Okay, you have to prepare something, go once. Prepare everything, go home back. Go to the office, prepare everything for a day or half a day or 1 hour or 15 minutes. Or you can use a robot for that purpose and then sit at home and then work from the lab. Work from home in the lab. A new normal. Therefore, the concept of work from home now has become work from anywhere. We have to thank the analytical instrument manufacturers to a great extent that they have come out with a new HPLC in the new normal or new instruments, the new normal. What do I mean by that? What they have done is, in the modern HPLC, they made you to work from home or work from anywhere. How to do that? They introduce a lot of automations. They use artificial intelligence because artificial intelligence as well as the internets all available in various fields, including robotic surgeries and so on. Now, can I borrow those technology and make a marriage between HPLC information technology? When they did this marriage, they use what is called cutting-edge technologies, machine to machine language, M2M, Internet of Things, artificial intelligence, machine learning. They make everything, they brought everything together, make it for realizing work from anywhere. When they did this exercise, they not only incorporated a lot of features, they also did the operation in such a way that it is safe, secure, and protective. Such a kind of environment they provided. And put everything together, we call it as modern HPLC. How to do that? What is that? I will show you a modern HPLC which we use in our laboratory. It is called Advanced Ray Series, given to us. I can operate through an iPad sitting at home. How to do that? Very simple. I will give an example. Before that, what are the issues that we face in our laboratory? The most important, as I just mentioned to you, preparation of the mobile phase. Second thing, you have to prepare your instrument for analysis, rinsing, washing, cleaning, and so on. Third one, I have to take my sample, weigh it, dissolve in a solvent, concentration in such a way, I have to use a burette or a pipette, or I have to take in such a low concentration, dilute it, make the volume, prepare a sample, or I have to extraction, I have to do what is called sample derivatization, all this exercise. So sample preparation. Then before I use any method, I have to develop a method. It is not just something readily available to you. You have to develop your own method. When you develop a method, we have to choose the correct method for the analysis. But our regulatory people won't keep quiet. Whether you work from home or work from office, maybe new normal, old normal, whatever it is, validation is a must. Verification of the validation is also a must to ensure the quality of your data. With all these constraints, you should be able to complete your analysis. Not sufficient. You have to process your data. You have to report the results in a format acceptable by every authority. This entire operations, how I do work from anywhere. And above all, security. We have to thank the manufacturers. They have developed and optimized a workflow. What this workflow says? They have made everything automatic. Right from sample preparations, right from the sample preparation, and then waking up the instrument for the date and time, and then make the instrument exchange of solvents automatically, thereby you keep the mobile phase ready. And then you also do all the analysis, sort the analysis, the auto shutdown you do, monitor it through your leader, your boss is sitting somewhere, monitoring data, everything can be done in a cycle where they have developed a workflow. Based on this workflow, lot of software they have developed, and all the softwares are internet enabled, secured, and it is operator specific and password protected. When that is the case, it can be used as a 360-degree automation system. When you do this one, not only that, it has got a lot of other features. One of the most important feature is when you work with instruments, all of us know there can be leak somewhere. There can be a sudden change in the pressure. There can be a sudden change in the injection. Then the instrument should be able to find out such a small variation, sudden jerks in the performance, and should have a judgment capability to auto adjust everything so that in between the runs, the instrument does not stop. Minimum human intervention. At the minimum thing, I keep the mobile phase. I don't even prepare. I keep 4 bottles, maybe water, hexane, maybe acetonitrile, maybe methanol. I can keep. How much I keep? How much I need for entire analysis for a week or so at least? I can keep that. And then I do a secure operation. All this is possible with the optimized workflow concept that has been introduced to us. The instrument which I use have this kind of features. Now, I will show an example. I come to the lab. I prepare for the analysis. First is standards and QC solutions. Sample pre-treatment and installation. Mobile waste preparation. Columns I fix. Start the analysis. Maybe an hour or so, or less than that. Sit at home. Monitor the sequence running. Data processing. And then I do what is called, after doing all these things, I switch off the instrument. Prepare the instrument for next analysis. Monitor and run the sequence. New normal. Social distance. I don't have to meet everybody every now and then, but I can communicate My job is uninterrupted. I can do everything. How does I do? We use what is called, how do I prepare the mobile face? If you see here, the workflow shows that mobile face, they use what is called a gravimetric sensor technology. There is a balance attached along with the tray. You calculate how much more you need, 5 liter, 10 liter, 2 liter, how much you want each mobile face. You prepare and keep it ready. For 1 week, you can keep it ready. You can keep in a bottle. There's such a software is available. You can, which will change as the mobile face volume comes down, the change in the weight will come down. It will inform you through smartphone or through a gateway or through your software. You can use 5 liter bottle or a 1 liter bottle, anything you can use. It automatically pre-checks the mobile face efficiency prior to start each of batch. It gives you an alarm or send to user's device a real-time information how much mobile face is left out for how many number of analysis. So you can completely monitor. It is enough you prepare once the mobile face and keep it ready. Rest of things automatically controlled. Such a kits are available. It is available in my instrument. Second thing, they use another software called Flow Pilot. What does it do? It avoids sudden jerk or excessive pressure in the column. What does it do? If I use a Flow Pilot software, it gradually increases the flow rate to half the set value, stays until the temperature reaches the set value, and gradually increases the flow rate. Therefore, my column does not undergo a shock. Everything smooth. My reproducibility is excellent. I can do very nice analysis. Great. Now I can keep a set of columns. I can use a 7 mobile face kit or a 4 mobile face kit. I can do whatever I want, and I can choose the column as a lake. Therefore, method development becomes very easy. So I have set of columns, set of mobile face, I have set of my samples, everything is done. Therefore, it is a quality by design I can do, and I can do the analysis. So I use analytical intelligence method for scouting, accelerating the screening, method development, and optimization with robust methods. I can use 6 columns, I can use 7 or 4 mobile faces for flexibility. Complete analysis is automated. The whole method development is automatic. Whether it's a QC lab, test lab, or an R&D lab. Very good. What does it do? Because of this, I can do multi-batch analysis. Multi-run, lot of samples can be analyzed. The productivity goes very high. Then another most important thing, I use what is called another software called Smart Method Scouting Solution software. What does it do? It does what is called, because of method scouting, not only that, when you do a complete method development, there are several ways by you make what is called report writing. A multi-data report is possible called MDR can be done, where fast-track method development and optimization and robot level methods can be leveraged with the power of multi-data report. You can choose which is the best method, automatically use the best method for analyzing. So such a smart scouting is possible with the software. Good. Now, I am sitting at Chennai, you are sitting at Mizoram or in Nagaland or in Bombay or in Jammu and Kashmir, or you are sitting at Ahmedabad. Can I transfer the method I have developed? I can do that. I can tell through the computer, transfer this is the best method, give it to my customer, he will use it. Seamless method transfer is called, it is called the separate software. You follow the USP, follows 621 chapter, possible. Anywhere. And also, it also completely, fully compliant to USP 621. So the pharmacopoeial method, for following the pharmacopoeial method, the quality is not compromised. That's the beauty of this. And therefore, you don't need revalidation. Just simply transfer your same technology, same instrument, same make, same model, no problem. It saves resource and time for a method development. Not only that, the analytical intelligence it possesses supports the accurate process and data intuitively, regardless of the user's skill. The reliable data is always acquired. It draws a baseline on its own because it does the peak threshold detection. It adjusts the system such a way, depending upon a threshold it defined, it gives you actual small peaks. You can do right integration. It can do baseline processing, peak integration, range it can do. Whatever you do sitting in the lab, it does automatically when you are sitting at home or sitting elsewhere, work from anywhere. This is called IP Finder software, information technology coupled with HPLC. This IPDA2 software, what does it do? When the chromatogram, you have a typical chromatogram where my impurity or related substance is merged with the main compound. You can see the circle, and there, if it is impurity, I can identify its impurity or a peak broadening by directly seeing the spectrum. It can capability of separating more than 2 peaks. It gives a spectral analysis of separated data for further confirmation. All these things are possible because of the advanced algorithms they provide through IPDA software, which we have in our case. Now you are reporting the software is called server connection. So because it is called server connection is available to you, you can couple the instruments, not only your HPLC, but also other instruments such as LC, UV, and so on. Client server connection. When you do this kind of activity with the FDA 21 CFR Part 1 guidelines, following this, all these data can be coupled through because of networking and full data integrity. It is possible for us to provide complete report automatically with this complete security protection. This is called lab solutions client server operation. All softwares, all information technology. Therefore, it is called as analytical intelligence, which gives you work flexibility. Whatever operations you talk about, it provides everything. It operates, monitor, instrument remotely, network for data security with work flexibility. Above all, it also controls the remote controls all the solvent operation, pump operation, etc. Now, when we do this kind of, and when you see the chromatograms, the most important thing is we generate a lot of data. When you do generate a lot of data, the biggest question is asked, to what way it can help my business activity? I have got, say, 1 lakh chromatograms. I have analyzed 1 lakh samples with various techniques, HPLC, GC, LCMS, FTIR, and so on. All these things can be put together. To what extent it is helping me to promote my business further, to make a, what we call it as effective business decision making. A large amount of data is needed. We call it as analytics, business analytics. The lab solutions, BIX, provides this information. A business analytic platform provides accurate lab insights with in-depth dashboards, for activities, asset utilization, thereby you maximize the asset in such a way, it enhances your presence in the business. It's a complete laboratory information. Caliber LIMS, Caliber QMS, DMS, Nicholson, so many softwares completely put together. We have a facility. We do everything through this. Say, above all, nowadays we have incorporated the QR also, so that this QR, if somebody takes a photograph and sees that, he can actually see how the instrument is running. You don't have to see the instrument. QR is sufficient, because you can see a YouTube picture through QR. Why not the instrument chromatogram? See, life is totally different. Really, it's a new normal. At least for me, at this age, I use all this facility. Therefore, to summarize, I have shown you a living HPLC with analytical intelligence, with industrial standard of work from anywhere, and then quality by design, analytics from everywhere. It has got a QR gated maintenance and so on. Therefore, it is your ingenuity to improve the art of measuring to ever high accuracy, precision, and your knowledge, which plays a very important role to enhance your success at every time, because you use all these facilities to make it successful in your efforts. Thank you all for your attention.
So we have a few more questions. I'll just read it out.
Yeah.
So Mr. Anil Sethi asks, there are some samples where it forms 2 peaks, but with the same parameter condition, it gives me 3 peaks. So why is this?
Repeat the question.
Sometimes when he injects a sample, it gives him 2 peaks, but with the same parameter condition, it gives them 3 peaks.
The same, if the same sample, if you do a duplicate injection, sometimes the column contains some other compound which is not eluted. It can do what is called a carryover job. Therefore, he has to repeat the analysis and then check it out.
So another question is from Prakash Arya. He says, when using the same brand column, why is the RT not matching?
Generally, when depending upon how many number of analysis is using, if a column is used for more than say 100 injections, the inlet port of the column is slowly getting contaminated. Such a contamination will be one of the causes for non-reproducibility of the column.
So another question is from Mueed. So his question is, which kind of chromatographic column is best for vetiver essential oil? I'm not sure what is vetiver essential oil.
Normally, it's a fatty acid. He has to use a FFAP columns.
Okay. So one from Quantum Drugs, he asked, there is a ghost peak also appears in the column. So how do we restrict ghost peaks appearing?
It is not a column problem, it's a detector problem. You have to check the detector flow through cell.
So another question from Mr. Prakash Arya. So he asked, what is the difference between the number of theoretical plates and the theoretical plates in meter?
Repeat the question.
So what is the difference between the number of theoretical plate and the theoretical plates in meter?
In meter?
Yeah. That's all is the question.
See, the theoretical plate is referred to number of theoretical plates is what we calculate using the formula 16 by H. When I say per meter, it means related to the length L, length of the column. It is represented by a number, so letter small n. And that number depends upon the length of the column. Larger the length of the column, n, the small n becomes low, resolution is better.
Okay. So we think we have time for just one last question. So one Mr. Thermalai asked, please suggest a good book for chromatography and specifically HPLC.
HPLC method development by Snyder.
Yes, sir. So I think we have now run out of time. So all the remaining questions we can answer to our participants. So I now thank all the participants for registering and attending this session. I also thank Dr. Venkat Manohar for this wonderful session on HPLC and the basics of HPLC and the new norm. So we'll end this session now. I just want to show you a small video about what the new AI series can do.